Okay. Good afternoon, ladies and gentlemen. I'm Neil Mitra. Welcome to this session at ARIA at reInvent 2017. It must have been a long day for you guys if you guys had been shuttling between all these different resorts. So we'll try to make it short so that you can go back to your drinks quickly. So let's get through it. Stephen Hawking once said, "We are all connected by the internet today, like neurons in a giant brain." And we are so excited to share with you a story of connected roads today, which will help portray how much more connected we will be in the days to come. Quick show of hands, how many of you here drive a lot or travel a lot? Okay, almost everyone, right? So this session is perfect for you because you will understand how in the future your travel could be more safer and more easier. I'm a solutions architect with Amazon Web Services. I help enterprise customers to migrate their workloads to the cloud, and that is as much fun as playing mini golf. I'm so lucky to share the stage today with Jeff Mangan from Panasonic. Jeff.
First of all, thanks for coming. I never had a chance to actually look at the registration, so I had no idea how many people were coming, and I figured as long as one person shows up, then that's all I could ask for, so good turnout. As Neil said, my name is Jeff Mangan. I'm a software engineer at Panasonic Automotive, and my focus is on connected vehicles and intelligent transportation systems. Living in Colorado, anybody here from Colorado? All right. Being in Colorado, I'm a snowboarder, mountain bike, jeeper kind of guy, so that's what I like to do in my spare time. Okay, so here's what you're going to learn today while you're here. First of all, what is connected vehicle technology? What is the current state of connected vehicle technology, which also includes architecture and challenges. Proposed future state with connected vehicle technology. And design patterns inside of AWS. We're also going to talk about hardware solutions, which includes roadside equipment, onboard equipment, which essentially is the hardware in the vehicles. And we're also going to talk about how you can build your own proof of concept. And in addition to that, we're going to show a little demo of what we built. So first of all, the history of Panasonic. It was founded in 1918 as Matsushita Electrical Industrial Corporation. Their first product wasn't invented. They've invented a battery-powered lamp, which originally was candlelit. So you could imagine having to go from, having to light that every day, going to a battery-powered. So that was pretty impressive back in the day. 1959, U.S. business was launched, and in 2008. The name was changed to Panasonic Corporation. As of 2016, they had approximately 250,000 staff, 580 subsidiary companies, and about 67 billion in USD revenue. One of those subsidiaries, the one that I work for, is Panasonic Automotive. They're a leading OEM of factory-installed mobile and audio equipment. Which includes head unit displays, which if you've ever seen a vehicle where you're actually staring at the window and you can see the control panels on the window, that's what a HUD is. They also do speakers and navigation modules. So as you can see here, Panasonic has relationships with many of the world's largest vehicle manufacturers. So potentially if you own a vehicle, Panasonic has probably worked on the infotainment system in that vehicle. You can see a lot of well-recognized brands here. So now I want to show you a video, short video on why myself and Neil are presenting to you today and the areas of traffic and safety management that we're working on improving.
just how far we can go in improving our nation's roadways. Thanks to CDOT's innovative RoadX program, the state had the foresight to see the opportunities technology could unlock. Together with Panasonic, they're developing the first production-grade connected roadway solution in the U.S. Starting with 90 miles of data-driven innovation along I-70, this solution will transform the state and the nation, giving roadway managers and drivers a whole new level of situational awareness. The expected results? Room for 4 times as many cars on the road, less congestion and frustration, less time spent in traffic, and less fuel wasted. And most important, up to 80% fewer crashes.
All right. So for those of you in Colorado, how many of you have heard of the I-70 freeway? I don't know if you've ever had the experience of driving up on Friday night, like pretty much everybody else in the state that likes to snowboard or ski in the winter. It's not a pleasant experience. That is essentially the area of our project that we're focusing on. So going forward, we should see a huge difference in those commutes, shortening those commutes and making things safer. How is connected vehicle technology going to help that situation? So we have some statistics from US DOT, Department of Transportation from 2013. As you can see, VDEX technology has numerous benefits. You can see here, from 2013, there were 5.6 million crashes and a little over 32,000 deaths from those crashes. Our studies show that with VDEX technology, we can prevent crashes, 419,000 crashes we can reduce. We can also avoid 5,000 fatal crashes. That's a lot of lives saved right there. I don't know about you, but I spend quite a bit of time commuting to my office every day. And in 2013, we spent 6.9 billion hours as a country in traffic. That's a huge number. So the goal is to reduce traffic time by 42% using this new technology and infrastructure. So recently I heard on the news that the cost of fuel was going up for the holidays. I don't know if any of you experienced that. My Jeep has 37-inch tires, so commuting to work every day gets kind of expensive. And our goal here, in 2013, we spent 3.1 billion gallons of wasted fuel. Our goal is to reduce fuel consumption by 22% and reduce the number of miles traveled by 20%. So connected vehicle data offers a wealth of information, including vehicle status and activities such as windshield, wiper status, traction control status, headlight status, and all of these things are already on vehicles today. All cars and light trucks sold since 1996 have had an OBD2 port equipped on that vehicle. So in general, this means any light truck or vehicle has been compliant with this since 1996 and even in late 1995. As far as the hardware for V2V communication, it's going to become an industry standard in the next few years. And as a matter of fact, in 2006, General Motors started testing this technology with their Cadillac vehicles. Other automakers working on V2V include BMW, Daimler, Honda, Audi, Toyota, Volvo, and others. And as you can see, nowadays a vehicle is essentially many independent devices. Look at all this data, everything from latitude, longitude, wiper status, as I mentioned, road friction, all kinds of information is available that we can leverage. So the vehicle itself can also now act as a mobile weather station with all of the additional technology that it has in it. And as you can see here, essentially what V2V is, for those who have never heard of that, essentially that's vehicle-to-vehicle communication. That's where two vehicles within range can share information with each other in real-time status. Vehicle-to-infrastructure is when a vehicle is able to broadcast information and the roadside equipment, the hardware that's installed on the road, is able to receive that information. And we also have infrastructure to vehicle, where the cloud system, for example, is able to send information back out to the vehicles. So how does connected vehicles, how does it work? It starts with and is built off of V2V communication. Messages are broadcast using what's called DSRC, direct short range communication. Messages are broadcast 10 messages per second per vehicle. So that's a lot of data. Roadside units can listen for and receive messages and forward that data onto the cloud. Input from other data sources, such as camera sensors, weather stations, and others, can also be collected and sent out to the cloud infrastructure as well. The cloud system is able to use that data collected, predict road conditions and other situational environments, and send messages back out to the vehicles as they're traveling along the road. So what data do we collect? There are two main V2X messages. One is PVD. One is a basic safety message. That message is transmitted, as I mentioned, 10 times per second from the onboard equipment, which is inside the vehicle. These BSMs are received by the roadside equipment while the vehicle is in range. In addition, while the vehicle is in range of the roadside equipment, the onboard equipment can receive a trigger from the RSU that tells it to start collecting information and store it, because the vehicle isn't always going to be within range of a roadside unit. You know, we would have to install so many of these, it wouldn't be practical. Eventually, once the vehicle becomes in range again with the next RSU, it is then able to pass that information back to the cloud along with any BSM data it's collected. And that's where the beauty of collecting all of this data comes into play, because we can use all of that data, process it, and essentially be able to cover all of the roadways without having to have these RSUs along the entire freeway. So what about data privacy? That's always a big concern. So what do we collect? Like I mentioned earlier, we collect vehicle state data, windshield wiper speed, direction traveled, whether your lights are on or off, airbag deployed. And the reason why we collect all this is, if you think about it, if your windshield wipers are on, then it's probably raining. You know, obviously, we don't want to base that off of 1, 2, 3 drivers. We collect that, analyze it. You know, if there's 50 cars on the road and 45 of them have their windshield wipers on, it's probably safe to say it's raining outside. Direction traveled, lights on or off. If it's daytime and the lights are on, probably a storm, heavy rain out there. We can also detect airbag deployed. There's been situations in the past where accidents have happened and they're not detected for a while. This could eliminate that by essentially notifying our system immediately. What don't we collect? We don't collect the VIN. We don't collect the make, model, color of the vehicle. We don't collect any owner information. That information isn't even available. These are all based off standards by IEEE and the Department of Transportation, and there's no way to get that information. It's essentially not even in the hardware. So with all the data that we'll be collecting, it was critical that we do some initial capacity planning. Obviously, you need to do that with any project, so that we could determine short and long-term needs. And so to do this, we gathered both public information and private information that my data science team had to collect from different agencies. And so doing that, we were able to evaluate what the average and peak data flow rates look like, evaluate the capacity needed to accommodate the messages, and evaluate the outbound data volume to the RCs. So doing that, we estimated about 2.12 billion messages per hour, or about half a gigabyte of data being passed across the wire into the cloud. For all of I-70 in Colorado, about 250 million messages per hour, or 3/4 of a gigabyte per hour. And for just the I-70 Mountain Corridor, where this project is initially focusing on, we're looking at 0.08 billion messages per hour, or 22 gigabytes of data. Now I'm going to turn it back over to my friend Neil, and he's going to talk about the current state of the architecture.
Thanks, Jeff. So as Jeff explained, there are different layers of communication in a connected road, right? Vehicles to vehicles, V2V, vehicle to infrastructure, V2I, and infrastructure to vehicles. So in today's session, we'll primarily focus on V2I and the I2V layers. So starting with V2I, let's dive into it. So vehicles on the road broadcasts telemetry data over a Wi-Fi spectrum to the roadside towers, also referred to as roadside equipments. The roadside equipments will be installed on the highways, starting with I-70 in Denver. So some of you were from Colorado here. You will probably not be surprised when you see this. And from the roadside equipments, once the data is captured, the data will be transferred over an encrypted fiber optics connection to the Department of Transportation data center, which has a pass-through router to send the data to the cloud. And this reference architecture could be very similar if you have other smart city use cases in mind as well. Probably the vehicles will be replaced by the light towers or the parking meters, whatever things you are trying to connect to. So as is the initial state of the project, and the goal was to get started quickly, the connectivity from the Department of Transportation data center to cloud was set up on VPN on IPv6. So the telemetry data passes through the VPN tunnel, it hits the Nginx load balancer, and these are essentially UDP packets. And Nginx load balancer then forwards the data to a ECS cluster. So ECS, if you're not familiar with it, is a managed service for running Docker. It stands for Elastic Container Services. So the services running on ECS does two key things: converting the data packets from UDP to TCP and converting the binary messages to JSON. And then the TCP MQTT messages gets published to the AWS IoT platform. So you might be thinking, why take all the trouble with UDP, right? Why just don't do it over TCP and MQTT? That is because this is a guideline set by DOT. So as per RSU specifications, UDP needs to be the protocol, so the anonymity of the vehicles stays. So once the data gets published to the IoT platform from the ECS, it happens over MQTT and TLS, right? It goes to the topics on the AWS IoT platform. Rules engine evaluates the payload, which has the telemetry data, and determines what is required, whether it needs to filter the data, whether it needs to transform the data, or whether it can just read out the data to a backend AWS service. So think of rules engine as the brain of the AWS IoT platform, right? And if you have any IoT use cases, rules engine will play a very crucial role for you, because it's the first point where you can do a lot of filtration, a lot of pre-analysis on the data. So consider a vehicle sending a payload with the temperature and wind data. It gets published to a topic, MQTT topic, on the IoT platform. Rules engine reads the payload. Rules engine runs an analysis using SQL queries. So you can run SQL queries with common functions like timestamp and absolute and conversion of ASCII to whatever. But in addition to that, rules engine also supports advanced functions like machine learning predict. If you want to do a real-time prediction on the data, you can do it with rules engine as well. And once the initial analysis is done, rules engine triggers an action to invoke an AWS service such as Lambda function, which could process the data and could persist the data to a backend data store. Rules engine also has integrations with other services like S3 and Kinesis and Elasticsearch, if that is something you guys need for your use case. So as Jeff was mentioning, you might have heard of incidents, right, in the mountains where people get stuck for days. And somehow they're not able to communicate to the emergency services. And even the emergency services do not have any visibility of what is happening, right? So the major goal, one of the major goals of this platform is to ensure there is real-time visibility to this type of incidents and a faster response time. So how do you do that? So we just talked about how the data is coming to the IoT platform from the roadside equipment. Once you have that, the rules engine publishes the telemetry data through the Lambda function and persists to a relational data store today. So RDS is a managed service for running relational database on AWS. That means you have zero administration, but not zero design. You still need to do design and performance tuning, right? Postgres was a natural choice because the use case has to support geospatial data. So once the data is persisted, it could be exposed via APIs or web applications running on the ECS cluster. And I don't know if you noticed during the video, there was a NOC, Network Operations Center, where there will be people sitting and monitoring it real time as well. So this data could be made available real time for those folks monitoring it and doing the needful. If there is a real time incident like a crash, and you don't want to go through that loop and waste time, with Lambda, you can send a notification using SNS. It can send email, SMS. So if there is a crash, if the road conditions are really poor, you can build that logic to act through Lambda as well. Excuse me. So Jeff showed the statistics earlier that we lost around 6.9 billion of hours in traffic and more than 3 billion gallons of fuel since 2013, right? So it's very critical for this project to analyze the data over an extended period of time to understand various patterns, various incidents, so they could be addressed. For example, after Thanksgiving in Las Vegas, there is reInvent and the traffic is huge, you need more help on the road. And there could be several events like this. So for enhanced data analytics, how do you do it? The data from the IoT platform can be persisted to S3. Anyone here who have not used S3 yet? No, okay, that's good. So you know that S3 is highly available, highly scalable, 11 nines of durability, right? So if you store 1,000 objects, you probably lose one in 1 million year. And that makes it a great solution for being a data lake because it has to be your single source of truth. And S3 supports different file format. It offers native integrations with services like EMR. So EMR processes the data from S3. It cleans the data, it transforms the data, it loads the data. It can use RDS if there are reference data there. And then you can run Spark, which is happening in the current state, but you have options to run anything, Peak or Hive or MapReduce or whatever you want to do. And once the data is transformed, the data could be further analyzed through Athena. If you have not used Athena, it's a serverless way of running big data analytics. It's built on top of Hive and Presto. And then the data could be visualized through Tableau or QuickSight or whatever BI solution your business, your data scientists are using. So now we talked about the vehicle to infrastructure layer, how you are getting the data, how you're using it from real-time analytics and batch analytics. Let's talk about the opposite way, the infrastructure to vehicle communications. And why do you need that? For example, if you are driving and you need to be notified that 2 miles from here, it's really foggy, or the road conditions are super poor, so you should drive slow or you should take a different route, and that notification comes to your vehicle directly from the cloud, from this platform. So how it happens, the data from the IoT gateway now takes the reverse path. So the conversion of the data happens from TCP MQTT to UDP. It goes through a forward proxy to the Department of Transportation data center to the roadside units from where it's broadcasted back to the vehicles. So now you understand the current state. Let's find flaws in it. Jeff and I love to do that. And if there is one takeaway from this session that you will have are the next 2 lines, or the next 2 buzz lines, I will say, data is the new oil. Or my friend Brian there, he loves to say, data is the new bacon. So you will see that the data volume will make this architecture that we just discussed less efficient in terms of cost, resiliency, high availability, and operations. So let's see how it does that. So as we know, the data goes over the MPLS connection to Department of Transportation. From there in a VPN tunnel, it's published to the cloud. But there are 2 problems with that. First of all, AWS does not support IPv6 on VPN natively today. So the team had to use their own VPN solution. That means they have to manage their own network infrastructure. They have to do all the capacity planning, right? And if they don't do that properly, if the traffic, if the volume suddenly goes to a spike, it could be a single point of failure. And that is bad. Also, VPN has limited network bandwidth because it's over the public internet. And then the data hits the load balancer. Nginx does the UDP load balancing. You might be thinking, why not Elastic Load Balancer? Because ELB does not support UDP today. It supports HTTP, HTTPS, TCP. There is another requirement, is that roadside units or the roadside equipments need to talk over static IPs. They can't talk over DNS. So we have a service called Network Load Balancer that we launched some time back, which supports static IP on a load balancer. But it still does not support UDP. So Nginx supports both those requirements. So the only problem there is related to cost. The Nginx free version does not support HA. And you have to pay licensing cost per instance. So every time you need to scale, you need another instance, you pay another licensing. And then the data hits the ECS cluster. ECS cluster can scale if you have configured it properly. It can do the conversion. But then it's an operational overhead. It's an additional hop, which introduces latency to this whole workflow. And if you have a real-time use case, you may not be able to afford this latency in your architecture. And finally, the data is published to the IoT platform, which scales on its own. It can support millions of devices, billions of transactions, so that is fine. For the real-time analytics, we saw that the data is persisted through a Lambda function to a RDS data store, right? I don't want to hurt the sentiments of any relational database fans here, but traditionally, relational databases are not great at scaling. So with Amazon RDS, it does support horizontal scaling through read replicas, it does support vertical scaling, but it's still a push-button scale. So if you have a multi-AZ, it happens probably on the standby, then it happens on the master. But still, you have to consider some time when the upgrade happens, even if you do a apply immediately, right? And for real-time use cases like crash and accidents, you may not be able to afford that 15 minutes, 20 minutes, 30 minutes upgrade of your database engine. For enhanced data analytics, this architecture looks great, right? You have a data lake on S3, and you have EMR. Customers love running Spark on EMR. It has a lot of capabilities. So what could be wrong here? For this use case, it's mostly structured data. You are not doing a lot of transformation. So we had to ask ourselves, is running EMR an overkill? EMR is a managed Hadoop for you, so you don't have to think about configuration, but you still have to think about the capacity planning. How many master nodes I need, how many core nodes I need, how many task nodes I need, what should be the configuration, M4, M3, blah, 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 right? Then you have to think, based, if you have a swim lane of jobs, whether I need a transient cluster or a persistent cluster so that you can save cost. Then you have to think about the cost optimization model. Do I need a reserved instance, on-demand instance, spot instance? How can I save cost? So we thought, is there a better way to solve this problem? Our CTO says, no server is easy to manage than no server. And we always try to keep that in mind. This is also a takeaway for you, probably. For the infrastructure to vehicle communication, all the pain points that existed on the way into the cloud exist on the back as well. You have an operational overhead with this conversion. You have a problem with HA, with cost. With VPN, there is a bottleneck, and then it goes back to the cloud. So now Jeff, who was so excited to understand the flaws, was not happy after finding all these issues. So we had to go back to the whiteboard. We had to do brainstorming and figure out what could be the future state architecture which remediates most of these problems. So let's start again with the vehicle to infrastructure communications layer. So vehicles on the road broadcast telemetry data to the roadside units. It goes over MPLS connection to DOT, back to the cloud. So what has changed? We introduced Greengrass. Anyone use Greengrass here? Okay, cool. So Greengrass essentially brings intelligence at the edge, at the roadside units. It brings all the IoT capabilities that we have on the cloud at the edge. So you have the MQTT broker, you have the rules engine, you have the shadows, right? And most importantly, you have Lambda. So you can do a lot of local compute at the edge. So how does that solve the problem here, right? And one more thing, if you have any use case where it doesn't make sense for you to send all the machine data back to the cloud all the time, then Greengrass could be a savior. Because remember, storage cost and compute cost were down substantially in the last few decades, but not the network cost. You are paying for all the bits and bytes, right? So if you can do offline processing and send only what is needed to the cloud, it probably gives you a lot of boost in terms of cost. And Greengrass can help you with that. So with Greengrass, we now do the conversion of the packets from UDP to MQTT at the edge, and even the raw message to the JSON. And then over an MPLS connection, we can send the data to cloud. Another thing changed here. We moved on to Direct Connect. There's no more VPN. Because Direct Connect solves the problem of the limited network bandwidth. It's a guaranteed bandwidth that you get. In addition, you can have multiple virtual interfaces that you can create with Direct Connect. You can still have a VPN as a failover if you'd like. And then the data gets published to the AWS excuse me, IoT platform. And suddenly, with just 2 tweaks, introducing Greengrass and Direct Connect, we have reduced so much complexity in that architecture. There is no Nginx to do the load balancing. There is no ECS cluster for doing the conversion. Because the data is coming over MQTT now, AWS IoT platform supports MQTT, and it's simple to manage. But at the same time, it's scalable and it's highly available. For the real-time analytics, now, the data could be published to Kinesis. So Kinesis is a managed service for processing real-time streaming data. Right? It scales completely with 0 downtime, whether you scale up or down. It replicates the data across 3 availability zones. You can replay the data. You can persist the data up to 7 days. You can build your custom applications because it provides the Kinesis producer library, Kinesis consumer library, or even you can use the Kinesis firehose. So you store the data to S3, which is your data lake, for future data processing. For real-time analytics, we use Kinesis Analytics. So you build a Kinesis Analytics application. If you want to do the aggregation of data over the sliding window, if you want to enrich the data from a relational data store or somewhere else, you can do all the stuff. And then you can persist the data from the destination stream using Lambda to a DynamoDB database. So one thing we talked about with the relational database is that it supports push-button scaling. But with DynamoDB, it supports low single-digit millisecond latency performance. At the same time, it supports auto-scaling. Right? And if you have to notify because of the crash and all the stuff, you can still do it on a real-time basis once the analysis is done through Kinesis Analytics, through Lambda. So the emergency services knows they have to go somewhere and do something immediately. For the real-time monitoring, the web applications, which is, again, used by the folks sitting in the network operations center and who have real-time, close to real-time visibility of all the roads, starting with Colorado, they will be able to see a real-time feed of the data. So they can subscribe to the topics over WebSocket and then render the website using the static assets from S3. So you can just build a serverless web application for your monitoring purpose as well. If the data needs to be consumed by other applications or third parties, you can build a REST interface using API Gateway. So API Gateway is a managed service for running your APIs. It integrates with various backend services, including Lambda. And Lambda can read the data from Dynamo, where you have already stored the data, right, from your real-time stream. For authorization and authentication, you can use Cognito and IAM. So with Cognito, you can use the federated identities for your APIs, for the web application, and even you can attach Cognito to an IoT policy. For enhanced data analytics, or the batch analytics, right, what do you do? So again, the telemetry data is stored into S3 now. And from S3, it can trigger through Lambda a job in Glue. Glue is a managed service for running ETL. It's cloud native, it's serverless, and it runs Apache Spark as its underlying infrastructure. So in the current study, if you remember, we had EMR running Spark. We are doing the same thing with Glue, but in a serverless way. Suddenly, all the capacity planning, everything that you had to do goes away, and you just focus on the job that you need to run on Glue. You just focus on the data processing unit or the DPU on the jobs. Glue also offers additional capabilities, like it has a crawler, which can crawl your data sources from time to time and figure out if there is a new feed, transform the data, and work on it. It also has a job scheduler, so you can build an orchestration workflow on Glue. But the piece I love most, and my customers, is a data catalog. So Glue helps you to store all your metadata, the operational metadata, the structured metadata, into a central metadata store, which is Hive compatible, drop-in replacement, that can be used by various services like EMR, Athena, Redshift, so you don't have to maintain separate metadata stores anymore. Glue can do that work for you. It also supports JDBC endpoints, so it can talk to your relational databases, Aurora, RDS, or even if you have a database on-prem. So we talked about the future state of the vehicle to infrastructure communication. Let's talk about the proposed future state of the infrastructure to vehicle communication layer as well. It's quite similar. It's simpler. So the MQTT data goes to the direct connect, to the edge. The conversion happens there using Lambda, and the data is broadcasted to the vehicles. Right? So now I talked to you about the software reference architecture. I will let Jeff take you through the hardware solutions and the lessons learned. Jeff.
All right, thanks, Neil. So I'm going to go ahead and get into some of the hardware issues and different aspects of the hardware side of this. So in addition to all our software development efforts, here are some photos that we've implemented at our Panasonic office, as I mentioned, in Denver. And you can see two of our test vehicles on the top left. You can also see the roadside units that we mentioned on the pole. You can also see some other hardware products that we looked at, evaluated, tested. And then you can kind of see a far back picture of what the hardware looks like when it's installed on a pole. It's about 17 feet up in the air. So doing this project, what we're doing isn't focusing on V2V or the vehicle side of it, but in order to actually do anything with this, we had to have vehicles generating data so that we could collect it. So in this project, we procured 4 vehicles, all brand new vehicles, and doing research, looking at the different usage patterns on the I-70, these are the vehicles we chose based off the type of vehicles that are driving up and down the I-70 freeway in Colorado. So you can see here we have a cargo van, we have a 300, we have a minivan, and we have a big SUV. So moving forward, there was lots of hurdles, cost, and complexities. So currently, BSM and PVD data is sent binary over UDP because of the current standards. So doing that required us to build a pre-processing layer which is able to send that to IoT gateway. So essentially doing that, we had to convert it to TCP from UDP. Another issue, hardware can be expensive and hard to obtain. This is all hardware that was made specifically for V2V communication and collecting on the roadway with roadside equipment. Installation and testing obviously required several steps. You have to put in the poles, you have to wire up the connection. And decoding binary data, doing that, we had to go through several iterations. We had to run it through our decoder, look at metrics, refactor the code, run it again, look at metrics, and continue to refactor it until we were able to achieve optimal performance. So doing all of this, presenting to you guys, what does this mean for you? How can you get into this? What can you do? It's not realistic for you guys to go out and get this type of hardware, invest the cost. Setting up this project, we had to build a test track. We installed 6 roadside units out by our office in Denver. We had to install fiber optics in the ground. get all of these RSUs installed 17 feet up in the air. And that was a lot of work. Not very cheap either. So as I mentioned earlier, all light cars and trucks starting in 1996 have what's called a ODB2 port. And nowadays, you can go out and buy an ODB2 port scanner, and you can plug it directly into that ODB2 port. And these you can go buy, there's Amazon. Anybody heard of that? Amazon.com. They sell them. You can go to your local electronics store. Everything from a few bucks up to 100. There's lots of different options. So you can get one of these. You can plug it directly into the ODB2 port. And the data is sent via Bluetooth to a Bluetooth-enabled device. And now you can go and build an app, run it on the phone, and collect the data from this ODB2 connector. As long as your mobile device is connected to a cell network, you can then transmit that data to the cloud, just like we're doing now. You can even use Greengrass, Raspberry Pi. There's theoretically a few different options you could go about doing this. And to be honest, the code out there, there's lots of example code out there. You just have to do a search for ODB2 port scanning with your favorite programming language, and you'll probably find it out there. One more thing I want to show you is, everything we've talked about so far is all about collecting data and sending it back, but we didn't really get into what are we doing with that data on the back end. And one thing you can consider as managing these roads, the Department of Transportation, their responsibility is to be able to understand what's going on in the roads and be able to react to that. So as this project got started, one of the big accomplishments that we worked on was building a web application to monitor this data in real time. And since you can't do a talk without a demo, now I'm going to show you what we created. So what this is this is a web app that the Department of Transportation can use to monitor and respond, send information back out to the vehicles. And so what I'm going to show you is a real environment where we had our 4 test vehicles driving around the track. One of our drivers simulated an accident. We couldn't convince her to actually create an accident, so we had to simulate it. And we're also going to show you how these vehicles interact with this information and how they can alter what they're doing based on that information. So what you can see here is vehicles driving around our test track. This information in real time is being collected, sent to the RSUs, and back to the cloud. And all of this is not staged. This is a real application that we created. And the first thing you're going to see is vehicle 1, the blue minivan, is going to simulate an accident. And what that's going to do is that's going to go to the RSU and back to the cloud, and it's going to immediately notify the DOT that there was an accident. And so we should see that in just a moment. And these screens here are real-time video capture of what the driver sees. And so now you can see that an accident was simulated. In order to show that to the driver, we kind of just made a broken screen on the display. And the next vehicle behind it received a direct V2V notification that there was an accident. So that happened, that was directly vehicle to vehicle. You can also see vehicles disappearing and reappearing, and those dots that kind of look like an inchworm scrolling along, that is the data that was collected as the vehicle is traveling out of range, and then once they get back in range to the next RSU, we then send it back to the cloud. And in order to show it on the screen, we just modeled it. Now you can also see the other two vehicles were notified of the accident as well. And one of them received it in advance so that it's able to determine if it wants to reroute where it's going. And the other vehicle was able to not only receive it via infrastructure back to vehicle, but it also received it in a V2V message as it approached that vehicle. Now what you see here is part of the application allows us to interact with other cities. So we can send notifications to other areas around Denver because this can affect multiple cities. We also are able to show a history of everything that's collected. So all of this information coming in and out, we capture it. And another critical feature is we're able to notify police, tow trucks, emergency services. We can do that in real time. So now, instead of somebody having an accident and having to wait, we're able to detect that in real time, and we're able to notify first responders and get them out there as soon as we can. So I'm going to go ahead and turn it back over to Neil, and he's going to walk through what you learned.
Thank you, Jeff. So what did we learn today? What is a connected vehicle technology? So we talked about the V2V, V2I, I2V. We talked about the challenges with the current state architecture. We talked about what are the patterns and design patterns, patterns and anti-patterns that we had to consider to come up for the future state architecture. We showed you how you can start building your own proof of concept using a Raspberry Pi or probably building your own mobile web applications. And these reference architectures, as I was mentioning before, could be leveraged for other smart city use cases you might have as well. And we'll be so happy if we hear from you, if you have any questions from today's session. We'll be here by the stage for quite some time, so feel free to come and stop in. We really appreciate all your time for taking this session and hope you have a wonderful reInvent ahead. Thank you.